Hi, y'all. I don't know if y'all can hear me. Let me just make sure. Okay, can you hear me? I think it should be good. My AirPods were acting weird, but should be fine now. Okay, I'm gonna go ahead and get started with a request that was sent to me via email, and that's to go over hybridization. So I'll start with that. I also got a request for endo versus exo, and on that one, I think I'm going to make a video. I don't really like the way that the Solomon's book explains it, and so I kind of want to look at a few other resources and use those to explain the endo versus exo a little bit better, but we can talk about that as well. But I'll start with hybridization and conjugation. So the main idea for hybridization is you have one s orbital and three p orbitals, right? But carbon is trying to form 4 bonds. So if you had the electrons evenly distributed in these orbitals to make bonds, it would be kind of weird. You'd have one really low energy bond and 3 higher energy bonds. So instead, it makes hybrid orbitals where it has 4 sp3 hybrid orbitals. And that's how you get that tetrahedral shape that we know and love, that's got the wedge coming towards you and the dash going away from you. Because there's 4 orbitals and they kind of have to be evenly distributed. So this is 4 sp3 hybrid orbitals. If you have 3 sigma bonds, then carbon has 1 pi orbital that's being used in a double bond, and then you have 3 sigma orbitals that are filled in, and those become just planar 3 sigma orbitals. Hang on just a second. So those 3 sigma orbitals, the 1s and 2p orbitals, are then a hybrid where you have 3 sigma orbitals made up of 3 sp2 hybrid orbitals together. Okay, and then the same thing if you have 1s, I'm running out of space here, and 1p, if you only have 2 sigma bonds, these other 2 p orbitals can be involved in the pi bonding. So the way I kind of like to think about that then is if you have four sp2 hybrid orbitals, each of these have one p orbital available, and that's what I've drawn here. So the carbon itself, these 3 sigma bonds on this carbon with the hydrogen, 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 this one has 2 hydrogens. These 3 sigma bonds are each made up of the hybrid orbital, but there is 1 p orbital that has actually got an electron in it, and the overlap of these p orbitals make your pi bond, right? However, when there's 2 orbitals like this overlapping right next to each other, there can also be overlap here between the middle. So actually, instead of just having 2 pi bonds where there's overlap, you sort of get overlap between all 3 of these, if that makes sense, or all 4 of those. So that's really what conjugation means, is that you have all these p orbitals that are in a row. And that's also why you have resonance stabilization, because if you look at the allyl radical or the allyl carbocation or the allyl carbanion, it has the same sort of breakdown here, where this is sp2 hybridized, so there's a p orbital that's left behind. This is sp2 hybridized, so there's a p orbital that's left behind. And this is sp2 hybridized, where there's a p orbital that's left behind. So really, instead of there just being a double bond and a radical off by itself, the radical is in conjugation with the other two p or pi orbitals, meaning that it's spread evenly around these three, so it's stabilized in that way. Same thing here, if there's a carbanion, it's stabilized. And here, if there's a carbocation, it's stabilized. The electrons can be evenly shared between those p orbitals. So that's a quick overview of hybridization and of aromaticity, and then, or hybridization and resonance, but that also plays into aromaticity. This didn't get fully dried. Because in an aromatic ring, all of these they have one hydrogen. So all these are sp2 hybridized, right? All of these are sp2 hybridized, meaning that there's a p orbital on each one. And so they can all overlap and share the electrons equally instead of there actually being alternating double bonds. And that's really what an aromatic ring is. An aromatic ring is stabilized by overlapping p orbitals. So that's a quick breakdown of why conjugation matters, what conjugation is, and how it plays into overlapping orbitals in aromatic rings and why we reviewed it. The other thing I got asked about was endo versus exo. I'm not going to do a huge in-depth review. I will just do a quick overview. If you start with an Diels-Alder, a ring that's fixed, and then you have some kind of aromatic or some kind of dienophile. So for a Diels-Alder, you have to start with a diene and a dienophile. And what I always do actually for Diels-Alder reactions is I break it down into sort of what is the main components. So I just draw out my diene and dienophile like this to make it a little bit easier to follow. And then I number. So 1, 2, 3, 4, 5, 6, because that's the basis for the 6-membered ring that's going to form. So I just go and number 1, 2, 3, 4, 5, 6. And then I draw this out. 1, 2, 3, 4, 5, 6. These electrons go here, making a bond there. These electrons go here, and these electrons go there, making 2 new sigma bonds. Sorry, I was off camera there. So it looks like this, where the 2 electrons from this bond form this bond right here. The 2 electrons from this bond form a pi bond right here. And the 2 electrons from this bond form a sigma bond right there between 4 and 5. So I'm going to go ahead and number 1, 2, 3, 4, 5, and 6. So I always do that first, and then I look at the substituents. So we have a cyano group, withdrawing group that makes it more electron loving, and then we have the bridge. So oftentimes what I do to start with, because this is bridged, I will do just the bridge within I don't worry about stereochemistry yet. I just do the bridge flat. And then I draw my 2 cyano groups, and I draw them either both as wedges or both as dashes, just to kind of show that they have the same stereochemistry. But this doesn't take endo or exo into account. And the best way I think to look at endo and exo is to draw the ring in this like sort of non-traditional way, where this is my carbon 1, 2, 3, and 4, my bridge between carbon 1 and 4. And then on 5 and 6, we have cyano groups, but we know that it's more stable for them to be pointing down. So I'll point both my cyano groups down. So then if I convert back to the ring structure, actually, if these are pointing down, they should probably be dashes to be the most stable version. And then these are sort of coming towards me. So these are like wedges coming out of the plane of the page. So this would be the endo form, because endo is when they point down. And then you do get the enantiomer, the exoform, but the exoform is not usually favored. So I will probably do actually a separate video on both of those, because I've had so many student requests for them, just so that they're up in the future. It looks like I don't have any new questions coming in, so I'll probably wait for a few more minutes. And if I don't have any new questions coming in, then I'll just go ahead and wrap it up.